Good afternoon everyone, I am Strish. Thank you for joining me for this video. We're looking here at how can we go from using these two basic reactants and end up with that. What do I have? I have methane and I have benzene. This is a representation of benzene. You know it looks something like this. You have these double bonds, but it's a conjugated pi system. And the double bonds can resonate between these two positions. Therefore, the general resonance structure looks like that because it's a representation of what that is. The true benzene molecule is this, not either of these because of the resonance, and this can be represented in a short manner like that. Hence, I use that. Given methane and benzene, how can we end up with this? Benzene, I have a CH, CH3, and NH and a CH3. What am I looking at over here? I'm looking here at a secondary amine. This is a nitrogen attached to two different atoms which are not hydrogens, but they're carbon atoms. It's a secondary amine. How can we generate that? Well, let's show you the procedure. Start here with methane. You'll have CH4 in the presence of, let's say, bromine diatomic, or you could have used iodine, or you could have used chlorine, but this right here is good. And ionizing radiation, you'll have CH3Br. Methyl bromide has been generated, a free radical reaction. In an SN2 substitution reaction, you can attack it with a nitrile, which is a C triple bond N. This right here is my nitrile. A nucleophilic substitution, it will attack this and it will displace the bromine, and you'll develop CH3C triple bond N methyl nitrile. We've generated methyl nitrile, and it's an essential step because it will help us develop the item which will be the stem from this benzene. So we've developed this. We have methane in a free radical reaction giving us methyl bromide, and in an SN2 substitution reaction with the nitrile we have methyl nitrile. If we were to take this item right here and undergo it with a basic reaction, hydrolysis followed by acid hydrolysis 1 and 2, in a basic environment followed by acidic environment, we can oxidize this to a carboxylic acid. It would be CH3 C double bond OOH. What is this? This right here is acetic acid or vinegar. We've developed this. Now what we're going to do is react it with thionyl chloride, SOCl2, sulfur, oxygen, 2 chlorine atoms, and we'll develop acetyl chloride, CH3 C double bond O Cl. I've developed acetyl chloride. Now look at this modification I'm going to make. I've started here from methane and I've ended up with acetyl chloride. I'm going to bring it over here because we've developed it and we're good. We've developed it, we've synthesized it. CH3 C double bond O Cl, acetyl chloride. We have acetyl chloride and benzene in the presence of AlCl3, a Friedel-Crafts acylation reaction. What we're doing here is an acylation reaction. Friedel-Crafts acylation. We have a chloride and a benzene in the presence of a Lewis acid. We'll develop here exactly what you would think. C double bond O CH3, this. It's a ketone. You have an R group here, you have an R group here, and a carbonyl group in between. It's a ketone. This is what I have. Now what I want to do is develop an imine. Look what I have over here, a CH3 NH2 methylamine, and you know this always has, nitrogen will have 2 electrons, a lone pair, but there are 2 electrons. It will attack right over here. I'll show you the mechanism at the end. What it will do is develop an imine, not an amine but an imine with an I, and when it does you're going to have this develop right here. You have this C double bond N and then CH3, and then you obviously have this CH3. One CH3 is here coming from your acetyl chloride, the other CH3 is coming here from your amine, and you've developed here an imine. What's an imine? A carbon with a double bond and nitrogen. It's an imine. So we've developed that. And now we're only one step away to our final product right over here. It's a reduction reaction. You have to reduce this double bond. Notice how you still have 2 lone pair of electrons here, but the hydrogen was lost. Here you have 2 hydrogens with the nitrogen, here you have none. Because they were lost in this reaction, a water was given away. How did the water come from? These 2 hydrogens right over here and this oxygen from the carbonyl, it gave you a water byproduct. Anyhow, we have that. We have to reduce it. In an oxidation reaction, you're bringing oxygen atoms into a molecule. In a reduction reaction, you're bringing hydrogen atoms into the molecule. And look at this, you have a hydrogen over here. What we will do is reduce it in the presence of a hydrogen and a catalyst, a metal catalyst. There are many ways. You can do iron in acid, you can do tin in acid, you can do H2 palladium, you can do zinc and acid, many metals along with some sort of acid which has a donatable hydrogen. which can help bring a hydrogen into your compound. But we are essentially doing here a reduction reaction, H2PD, hydrogen diatomic and palladium catalyst. It will reduce this double bond, bring a hydrogen, and you'll come here to your end product. We have to talk about this, the mechanism, and we will, but let's name this compound. You've seen it. We have over here a secondary amine. You want to name it based on that amine. This amine, if I reconfigure it like this, I have a methyl group and then I have all of this attached to this nitrogen. This right here is the largest item, this right here is the smallest item, so we can start with that. It's an N-methyl. That indicates that there's something attached to an amine. I have an N-methyl. Now we have to name this part right over here, the large part. This large part has a benzene with an ethane, or you can say you have an ethyl group with a benzene attached to it. The benzene is attached obviously to position 1, and the amino group is attached to position 1 of this ethane. You can call this 1, this right here is 2. You have benzene attached to it, you have nitrogen attached to it. So we can parenthesize it because we have a little bit of a compound here to write. To clearly distinguish the fact that we have benzene attached to carbon 1, we can say 1-phenyl, right? Because the phenyl group is attached to carbon 1 of this ethane. Now we have to somehow tie it in with this. And this part right here will be ethanamine. From ethane, you have ethane, then amine, ethanamine. There are multiple ways of naming it, but this is one way. N-methyl 1-phenyl ethanamine. Meaning the amine group is attached to your ethane. It's assumed to be at carbon 1 because everyone numbered it. And you know the benzene is attached to carbon 1 of this ethane. And to that amine, we have an N-methyl attached. N meaning is attached to your nitrogen, a methyl is attached to your nitrogen, but it's part of your amine. So N-methyl 1-phenyl ethanamine, and we're good. And this right here will be the name of this compound. Now that we've looked at the synthesis reaction, let's very quickly look here at this imine mechanism. It's interesting. At a minimum, we can use a ammonia, but let's use primary amine. Your primary amine is exactly this, RNH2. Keep in mind, nitrogen will have its lone pair of electrons and you have to represent it properly. This is what we have, RNH2, a primary amine. It's looking here or seeking out a carbonyl group. And why would it be doing that? Because the nitrogen is a very good Lewis base. Because of the dipole moment in the direction of electronegative oxygen, you have a partial negative, you have a partial positive. This carbon is charge deficient, or it can behave as an electrophilic site for a Lewis base or a nucleophile, and it can attack. With the shuffling of electrons, you can end up here at this next step. I will represent the nitrogen like this now, RNH2, that's what it is. It's going to be a deficient species with a positive charge because it has lost its complete set partially to a development of a nitrogen carbon bond. Those two electrons are right here, as you can see. Because it's lost that electron or the set to this bond, it's become charge deficient. You have over here the oxygen coming like this, which will be charge excess. Here are your other two stems, as you see. We have that good representation, neutral, neutral, and neutral. Charge has been maintained, it's balanced. The shuffling of electrons has brought us to that step. Now what we will do is remember that at the end of this reaction, we must see at least a water molecule be removed. It can either come entirely from these compounds, or it can come partly from the medium, and I'll tell you. The oxygen will come directly from here, one hydrogen will come from here. Sometimes the other hydrogen come from the compound, but the other hydrogen, the second hydrogen, can come from the medium, and I will show you that particular fact in this mechanism. What will happen over here is this. You are looking here at this oxygen, which will use two of its electrons to snatch this hydrogen. The electrons from this bond will return back to nitrogen, and nitrogen will regain its lone pair, and it will look as this. You have nitrogen, you have the lone pair coming back. The bond electrons have come back, the oxygen has stolen that hydrogen, and you have this. Oxygen is no longer charge excess because it has lost some of that charge density to the development of this bond. This is what we have right over here, and it's a good end result. Everything should be a neutral compound. You have neutral here, you have neutral here. Charges are neutral, but here you have neutral as well. What we need is this OH to escape, and how can we make this OH escape? By making it into a good leaving group. How can we do that? In an acid environment. We will protonate that OH. The oxygen will seek it out and it will get protonated. You will have this. You still have the nitrogen, hydrogen as this. You have the lone pair electrons, but now you've protonated the oxygen and it looks something like this. You've lost two of its electrons to the development of the bond, hence it's charge deficient. You have here a water molecule, a protonated hydroxyl group. This hydroxyl group will depart. And you can very much call this your water molecule, which is going to be at the end. The only reason I was stressing on the fact that we will have a hydrogen coming in from the medium, I will talk about that momentarily. But this right here is our water molecule which will escape. These two electrons of the nitrogen will come back over here to generate a nitrogen carbon double bond. The water molecule will escape. Your result will be this. You're looking at RNH, but you have an imine forming, and you have this with the loss of the water molecule, as you see, and here's a water molecule, but it's not going to be as this. Momentarily I'll talk about it because the acid has to be regenerated. Keep in mind now we have 4 covalencies to the nitrogen and has become charge deficient. The reason being it lost 2 of its electrons to the development of a nitrogen carbon bond. A double bond has formed. Original singlet, now we have a duplex over here. But this right here is not imine. This right here is iminium ion. Iminium ion. But this iminium ion will yield our imine. And I'll show you how. We have to return nitrogen to its natural state, where you are looking here at the lone pair of electrons. The way it can do that is you have this water molecule. I'll represent that water molecule as this. You have the water molecule which will use 2 of its electrons to snatch this hydrogen. The electrons from this bond will go back to nitrogen. This right here will leave as a protonated water molecule, and you'd say H3O plus. This is where I was talking about. Sometimes the hydrogen can come from the medium, sometimes the hydrogen comes from the compound, but definitely the oxygen and 1 hydrogen at least comes from your initial reactants. We have a protonated water molecule, hydronium, acid is regenerated. In essence, what you really see at the end result of this reaction is a hydronium ion, technically. Not just water, but hydronium, because the hydrogen has to be, or the acid has to be regenerated. When you do this, the electrons come back to the nitrogen, you've developed your end result, which is your imine. The electrons coming back from this bond right over here. You have your imine, and this is it. Look at the valency of the nitrogen, it's 3, you have 1 over here, 2 over here, it's perfect. This right here is your mean, and it's your end result, along with the hydronium. Because the hydrogen ion is too short acting of a species, the actuality you see is the hydronium, a protonated water molecule. This water molecule and becoming protonated from one of the hydrogens, becoming hydronium. Technically, if you were to argue, you can say one oxygen is coming from here, a hydrogen is coming from here, and a hydrogen is coming from here, but also a hydrogen is coming from the medium. But it's occurring in such a intricate way, you can say it's partly coming from the medium, partly coming from the compound, but the end result byproduct is a hydronium. That's it for this mechanism. Thank you for watching.